Tonight, we're diving into the deepest riddle in modern physics, one that even Einstein couldn't solve. At the heart of black holes and the birth of the universe lies a terrifying contradiction. Two of our most successful theories, quantum mechanics and general relativity, completely break down when used together. If one is right, the other must be wrong. Or worse, we're missing something entirely. This isn't just science, it's a battle for the soul of reality. In the world of the very small, particles dance in quantum fog, appearing and vanishing in a haze of uncertainty. But in the vast arena of planets, stars, and galaxies, gravity reigns supreme, bending space and time like a cosmic puppeteer. These two descriptions of the universe have stood the test of time, yet when you try to use them together, everything falls apart. So tonight we ask the question that has haunted physics for a century: is quantum gravity even real? What is it? Why haven't we seen it? And could it finally unlock the ultimate theory of everything? From the mind of Einstein to the edge of the universe, we'll explore black holes, evaporating stars, vibrating strings, looped-up space-time, and the mysterious Planck scale, where reality itself may be woven from something stranger than space and time. This is the story of one of science's boldest quests, and the frontier that could redefine what it means to exist. So lean in, because what you're about to learn may challenge everything you thought you knew about the universe, and reveal that the laws of reality are still being written. What if the universe is missing its most important equation? Not because we haven't looked hard enough, but because our best theories are whispering two different answers to the same question. On one hand, we have the elegant curve of Einstein's general relativity, a theory that redefined gravity not as a force, but as the very shape of space-time itself. On the other hand, we have the chaotic dance of quantum mechanics, where uncertainty reigns, particles flicker in and out of existence, and nothing is truly certain until it's measured. Both of these theories have shaped our modern world. One powers GPS satellites and explains the orbits of planets. The other fuels lasers, semiconductors, and quantum computers. But when these two theories meet, at the edge of a black hole or in the first moments after the Big Bang, they fall apart. This is the central puzzle of modern physics. The great unanswered question: can gravity, the warping of space-time, be described using the same quantum rules that govern atoms, electrons, and photons? If so, what does that mean for our understanding of the universe? And if not, what new physics awaits us beyond the known? Quantum gravity isn't just a concept, it's a battle between two titans of science. It's Einstein versus the quantum, continuity versus uncertainty, geometry versus probability, and for over a century it has resisted every attempt to unify it. Imagine for a moment standing at the edge of a vast canyon. On one side, Einstein's theory carves the terrain in sweeping, majestic curves. On the other, quantum mechanics fractals downward into strange, probabilistic patterns. Somewhere, deep within the canyon's foggy abyss, lies the theory that connects them. It's not just about reconciling the big and the small, it's about discovering what the universe is really made of. Not matter, not energy, but the underlying rules that allow matter and energy to exist in the first place. Physicists have a name for this quest: quantum gravity. And for many, it's the holy grail of modern science. A single framework that not only explains the behavior of particles and fields, but also explains how space and time themselves arise. A theory that bridges the gap between the macroscopic world of stars and galaxies and the microscopic world of quantum fields and forces. A theory that, if found, could reshape our understanding of everything, from the birth of the cosmos to the death of black holes. But make no mistake, this is not just about solving a puzzle for the sake of curiosity. There are real consequences for not knowing. Without quantum gravity, we cannot explain the singularity at the center of a black hole, where space-time itself is predicted to collapse into a point of infinite density. We cannot fully describe the first fractions of a second after the Big Bang, when quantum effects and gravitational effects were equally dominant. We cannot even be sure that our current theories are correct in the domains they claim to rule, because until a deeper unifying theory is found, we live with a contradiction at the heart of reality, a contradiction that so far no equation has resolved. And yet the effort to find this theory has led to some of the most profound and creative ideas in physics. String theory, which imagines that particles are actually tiny vibrating loops. Loop quantum gravity, which reimagines space as a web of interconnected loops that evolve over time. Causal set theory, where space-time is built from a collection of discrete events. Asymptotic safety, emergent gravity, holographic duality. These are not just fringe ideas, they're serious attempts to rewrite the rules of reality. They all share a common thread: the belief that space and time are not fundamental, that what we experience as smooth, continuous space-time is actually built from something deeper, something more granular, more mysterious, and more quantum. In this series, we'll explore these ideas in depth. We'll trace the origins of quantum gravity, starting with Einstein's own attempts to unify gravity with electromagnetism. We'll meet the physicists who risked their reputations to chase this elusive goal. We'll examine the mathematical tools they developed and the philosophical implications that emerged. Because at the heart of quantum gravity is not just a new set of equations, but a new way of thinking about existence itself. We'll see how black holes have become laboratories for testing these ideas, how Hawking's prediction of radiation from black holes opened a doorway to quantum gravity, how the information paradox challenged everything we thought we knew about entropy and determinism. We'll travel back to the earliest moments of the universe, when quantum fluctuations were amplified by inflation to become the seeds of galaxies. And we'll look ahead to the experiments that might finally offer clues: gravitational wave detectors, space-based observatories, and quantum simulations. But perhaps most of all, we'll embrace the uncertainty, because the search for quantum gravity is not a straight road. It's a maze, a labyrinth of hypotheses, dead ends, and revelations. Theories rise, collide, and sometimes merge. Rival camps argue over first principles. Data remains elusive, and yet progress is made, slowly, patiently, through a combination of mathematical elegance, physical insight, and sheer persistence. In the words of theoretical physicist Lee Smolin, every deep question in physics has an answer that is both beautiful and unexpected. Quantum gravity is no exception. Whatever lies at the end of this journey, whether it's strings, loops, or something we haven't yet imagined, it will be beautiful, and it will be unexpected. So this is our starting point, a fork in the road between the cosmos and the quantum. A challenge handed down from Einstein and Feynman, Hawking and Wheeler, a story that begins with a paradox and might end with the ultimate unification. As we set out, keep this in mind. We are not just looking for new particles or new forces. We are looking for the source code of the universe. And perhaps, just perhaps, we are getting close. Albert Einstein didn't believe in quantum mechanics. Not fully, not deeply. He accepted its predictions, of course. He acknowledged its success. But in his bones, he was convinced that something was missing. That nature at its core was not random. God does not play dice with the universe, he famously wrote. And yet, the universe kept rolling the dice anyway. The very theory that would one day challenge his beloved relativity was already gaining ground. And Einstein saw the conflict coming before almost anyone else. But long before quantum gravity became a phrase whispered in the halls of theoretical physics departments, there was only Einstein's gravity. In 1915, his general theory of relativity redefined everything we thought we knew about space, time, and motion. Newton had said gravity was a force. Einstein said gravity was geometry, the warping of space-time by mass and energy. It was a triumph of mathematical beauty. When the theory was confirmed in 1919 during a solar eclipse, bending the light of distant stars around the sun just as Einstein predicted, he became a global icon. But even then, questions loomed. A year later, Einstein published a paper on gravitational waves, ripples in the fabric of space-time itself. If mass could warp space, then moving mass could send waves through it, like pebbles tossed into a pond. He doubted they'd ever be detected, and for 100 years they weren't. But the idea itself opened a door. Gravity wasn't static. It could move, vibrate, carry information. These were not just consequences of his equations. They were glimpses of something deeper. Gravity might have dynamics. It might be quantizable. And Einstein knew it. Quietly, behind the scenes, he began to wonder whether gravity could be unified with the newly emerging quantum theory. In 1916, just a year after relativity's debut, he began exploring how elementary particles might arise from the gravitational field itself. He even suggested that mass might emerge from curvature, a radical idea at the time. The seed was planted. Gravity and matter might be two sides of the same coin. Meanwhile, quantum theory was stirring. In 1905, Einstein had proposed that light came in discrete packets, quanta, which would later be called photons. This wasn't just a clever way to explain the photoelectric effect. It was a profound hint that nature, at its most fundamental, might not be smooth and continuous, but made of tiny, indivisible chunks. In the 1920s, the quantum revolution accelerated. Heisenberg's uncertainty principle, Schrödinger's wave equation, Dirac's relativistic electron, a whole new language of reality was emerging, one that didn't mesh with Einstein's classical spacetime. And this was the root of the coming crisis. Quantum mechanics described the behavior of particles. Relativity described the behavior of spacetime. But what happens when the particles have mass? When they warp space-time, when their behavior is governed by probabilities but they're tugging on a deterministic fabric? The equations didn't agree, the logic didn't match, and at the core there was a philosophical divide. Einstein's universe was smooth, local, and continuous. Quantum mechanics was grainy, probabilistic, and, most disturbingly, non-local. By the 1930s, Einstein's frustrations had crystallized. In a famous 1935 paper with Boris Podolsky and Nathan Rosen, he introduced what's now called the EPR paradox. The point was to show that quantum mechanics couldn't be the full story. It predicted correlations between distant particles that seemed to violate causality. To Einstein, that was unacceptable. He believed that hidden variables, deeper, unseen rules, must exist to restore order. But his paper had the opposite effect. It inspired the very experiments that would later confirm quantum weirdness and deepen the mystery he was trying to resolve. That same year, Einstein began working with Peter Bergman on a new approach to unifying gravity and electromagnetism. It didn't work. The equations became tangled, the math exploded into infinities. But the effort mattered. For the first time, physicists were explicitly trying to apply quantum principles to the gravitational field. They were asking, what happens when space-time becomes uncertain? When the geometry of the universe itself is a quantum variable? One of the earliest physicists to seriously attempt this was Leon Rosenfeld. In 1930, Rosenfeld published a paper attempting to apply the techniques of quantum field theory to gravity. He tried to quantize the metric, the mathematical object that defines spacetime's curvature. It was a pioneering step and a painful one. The calculations spiraled into infinities. The physical meaning became murky. Quantum field theory worked beautifully for electromagnetism. For gravity, it collapsed under its own weight. And yet, the question lingered. Could gravity be a field like any other, with quanta, interactions, and perhaps even a force-carrying particle? The idea of the graviton, a hypothetical massless particle that mediates gravity, was born in these early years, more as a mathematical placeholder than a physical entity. but it planted the idea that gravity, too, might come in discrete units, that space-time could ripple in quantized steps, that the fabric of the cosmos might be made of threads after all. Einstein, for his part, never fully embraced these ideas. He continued to chase a unification of fields, but he resisted the probabilistic nature of quantum theory to the end of his life. In letters and lectures, he spoke of the incompleteness of quantum mechanics, his belief that a deeper theory would one day replace it. Ironically, that deeper theory may be quantum gravity itself. By the 1950s, a new generation of physicists began picking up the threads. John Archibald Wheeler, Bryce DeWitt, and others started to explore what it would really mean to quantize spacetime. They were building on Einstein's legacy, but moving in a direction he never quite accepted. They embraced the uncertainty. They welcomed the paradoxes. They began to ask, if quantum mechanics applies to everything, then it must apply to gravity too, and to space, and to time. And so the stage was set. The first cracks had appeared. The old theories, brilliant though they were, could no longer explain everything. A new theory was needed, one that could unite the curvature of the cosmos with the jitter of the quantum. But such a theory would require more than clever mathematics. It would require a complete rethinking of what reality is. By the 1930s, the world had begun to realize that physics was standing on a precipice. General relativity had reshaped the very stage upon which the universe played out. Quantum mechanics had rewritten the script, but no one could figure out how to get the two to speak the same language. Einstein, now in his final act, was still chasing unification, not of ideas, but of forces. He sought a single equation to govern gravity and electromagnetism, perhaps even to explain the particles themselves, but he was running out of time and out of allies. The younger generation was seduced by quantum mechanics' precision and success. Einstein, to many of them, seemed to be fighting shadows. But there were a few who saw what he was reaching for, not as folly, but as foundation. Leon Rosenfeld was one of the earliest to walk this path. In 1930, he tried to bring quantum mechanics to the gravitational field, not symbolically, not philosophically, but mathematically. Rosenfeld took the Einstein field equations and tried to treat the gravitational field like any other quantum field, applying the canonical quantization procedures used in electrodynamics. It was the first serious attempt to turn gravity into a quantum theory. The result? Infinities. Not the poetic kind, but the disastrous mathematical ones. Every attempt to quantize the gravitational field resulted in terms that exploded to infinity, rendering the predictions meaningless. It was discouraging, but it revealed something important. Gravity, unlike the other forces, was non-linear. The equations that governed it weren't easily tamed by the tools of quantum mechanics. They twisted back on themselves. They fed their own curvature into their own equations. This self-referential nature of gravity, its refusal to be isolated from the very space-time it shaped, would haunt quantum gravity research for decades. Still, others pressed on. Peter Bergman, a student of Einstein, worked through the 1930s and 40s to develop a consistent framework for unifying quantum mechanics and gravity. Along with Einstein himself, he explored generalized field theories, mathematical constructions that tried to extend general relativity to include the electromagnetic force. Some were promising, most were not. The equations became increasingly complex, the geometry ever more abstract. And while Einstein and Bergman hoped to discover new physical insight, they were increasingly accused of constructing mathematical castles in the clouds. But their efforts were not in vain. In the process, they unearthed something deeper. The incompatibility between general relativity and quantum mechanics wasn't just technical, it was philosophical. Quantum theory required an external clock, a background of space and time against which events could unfold. Relativity said no such clock existed. Time itself was part of the gravitational field, not something outside it. This contradiction would soon give rise to one of the greatest paradoxes in theoretical physics, the problem of time. By the 1950s, the torch was passed to a new wave of physicists, eager to modernize and formalize the vague attempts of the previous generation. Among them was John Archibald Wheeler, an American theorist with a poetic soul and a mathematical mind. Wheeler didn't just want to calculate quantum gravity, he wanted to understand it, to feel it, to visualize the universe not as a backdrop, but as a dynamic entity, constantly in motion, even when it seemed still. Wheeler's approach was bold. He coined the term geometrodynamics, a vision in which space-time itself was the only substance in the universe. Matter, energy, particles, these were just vibrations in geometry, hills and valleys in the terrain of space-time. If that was true, then quantum mechanics had to apply to geometry itself. The curves, the warps, the expansion of space, all had to be probabilistic, fluctuating, uncertain. In this view, the universe was a quantum object from top to bottom. Working alongside Wheeler, physicists like Bryce DeWitt took the next step. They built the mathematical scaffolding for what would become the canonical quantization of gravity. And in 1967, the breakthrough came, the Wheeler-DeWitt equation, an elegant, terrifyingly simple equation that attempted to describe the quantum state of the entire universe. It had no time variable, no clock, no ticking moments, just a wave function for the universe itself, a timeless, all-encompassing probability field. But it introduced a new problem. If the wave function of the universe doesn't evolve in time, then where did time go? This was the problem of time, a deep and unresolved paradox in quantum gravity. In quantum mechanics, the Schrödinger equation tells us how wave functions evolve over time. But in general relativity, time is just a coordinate. It can be bent, slowed, frozen. So when the two are brought together, time itself seems to vanish. The Wheeler-DeWitt equation describes a universe that doesn't change, an eternal quantum soup. But we clearly experience change. We see the universe evolve, stars are born, galaxies collide, we age. So how can time emerge from a theory where time doesn't exist? Physicists began to explore whether time might be an illusion, a secondary phenomenon that arises only when parts of the universe are compared against each other. That perhaps there is no universal now, only the relative unfolding of one part of the cosmos against another. If true, it would mean that quantum gravity doesn't just rewrite the rules of motion, it rewrites the very concept of reality. Past and future would be perspectives, not absolutes. The universe, in this view, would be a frozen block of possibilities in which time emerges like a shadow from the motion of subsystems. Wheeler loved this kind of thinking. He spoke of the participatory universe, a cosmos where observation helped bring reality into being. He explored concepts like quantum foam, the idea that at the smallest scales, space-time might froth and bubble with uncertainty, that the smooth, continuous geometry of Einstein's equations was only an illusion, like a pond that looks glassy from afar but is teeming with activity up close. It was a deeply unsettling vision, but it set the stage for everything that followed. By the early 1970s, the dream of quantum gravity had taken on a new shape. It was no longer just about adding quantum mechanics to gravity. It was about reconstructing the entire architecture of the universe, from time to space, from particles to fields, from matter to geometry. The dreamers of the early quantum gravity era had laid the foundation, often stumbling, often guessing, but always reaching towards something deeper. And though Einstein would never see it, the revolution he helped ignite was now moving in directions he could scarcely have imagined. By the mid-20th century, gravity was no longer just a force. It was a question, a puzzle that refused to yield. And into that puzzle stepped two minds, John Archibald Wheeler and Bryce DeWitt, determined not just to solve it, but to understand its meaning. Where others saw a mathematical inconvenience, they saw a philosophical frontier. The goal wasn't simply to quantize gravity. The goal was to understand what the universe becomes when you try. Wheeler, ever the cosmic poet, had long championed the idea of geometrodynamics, the notion that the universe is made not of matter, but of shape, curves, distortions, ripples in the very fabric of space and time. He believed that everything we see, particles, light, even the concept of time, could emerge from the undulations of geometry. But to move from idea to theory, he needed the machinery of quantum mechanics. And that's where DeWitt came in. Together, they built a framework that would shake the foundations of physics. It began with a deceptively simple question: what happens when you try to apply the rules of quantum mechanics not to particles within spacetime, but to spacetime itself? In 1967, their answer emerged: the Wheeler-DeWitt equation. A single expression meant to encapsulate the entire universe as a quantum object. Instead of asking how particles move through space, it asked how the geometry of space itself fluctuates. Instead of a wave function describing a single particle, the Wheeler-DeWitt equation described a wave function of the universe. And then came the twist. There was no time variable. In conventional quantum mechanics, the Schrödinger equation describes how a system's wave function evolves over time. Time is the river. The wave function is the boat. But in general relativity, time is part of the riverbed. It bends, twists, slows down. So when you quantize the whole river, you lose the boat entirely. There is no external clock, no universal tick, just a vast, silent probability cloud describing all possible configurations of space. This is what physicists mean when they say the Wheeler-DeWitt equation froze time. It's not poetic exaggeration, it's literal. The equation describes a timeless cosmos, an eternal now, in which every possible history, every possible future coexists in superposition. And yet we experience time. We see the sun rise and set. We grow older, stars are born, galaxies collide. So where in this frozen quantum picture of the universe does change come from? This question, the problem of time, is one of the deepest puzzles in all of theoretical physics. And it's not just academic, it's existential, because it strikes at the very core of what it means to exist. Some physicists propose that time is an emergent phenomenon, something that only appears when we zoom out. Much like temperature doesn't exist for a single atom, but emerges from the collective motion of many atoms, time might not exist for a single quantum universe. But it could emerge when we look at the relationships between parts of the universe. In this view, the illusion of time arises from the entanglement of subsystems, when one part of the universe acts as a clock and another responds to it. Others suggest that time might not be fundamental at all, that it's a human construct, a way of stitching together moments in a story we tell ourselves. The universe, they argue, is a static, four-dimensional block. Past, present and future all equally real. What we call now is simply a slice through that block, a perspective, not a property. Wheeler himself toyed with even more radical ideas. He spoke of a participatory universe where observation plays a central role in shaping reality. In this view, the act of measurement doesn't just reveal information, it helps define what is real. The observer, in a sense, creates the observed. And so perhaps time arises only when something conscious is there to notice it. Bryce DeWitt, more rigorous, grounded the theory in mathematics. But even he admitted that the implications were staggering. The Wheeler-DeWitt equation doesn't give you snapshots of a universe evolving in time. It gives you the entire reel, all at once. Every possible geometry, every possible history. The task of physics, then, becomes not tracking motion through time, but understanding the structure of this vast configuration space. To make sense of this frozen landscape, physicists introduced the concept of superspace. Not the space we live in, but a space of all possible three-dimensional geometries, a kind of metaspace where each point represents a different shape the universe could take. The Wheeler-DeWitt equation defines a wave function over this superspace, assigning probabilities to different geometrical configurations. But without time, how do you move through superspace? You don't. Instead, motion becomes a relation. Change is no longer about shifting positions in time. It's about comparing different configurations. It's a relational universe, where what matters is not when something happens, but how one thing relates to another. To visualize it, imagine a vast library not filled with books, but with snapshots of every possible universe. Each book is a complete, static image, no pages, no sequence, just a single frame. The Wheeler-DeWitt equation doesn't tell you which frame is next. It tells you which frames are most likely to exist. And we, as conscious observers, experience these frames as flowing one into another, giving rise to the illusion of time. This approach isn't without controversy. Many physicists find it deeply unsettling. A universe without time, without change, it violates every instinct, every lived experience. But the math doesn't care about instincts. Others have tried to modify the Wheeler-DeWitt equation, introducing parameters that restore a kind of internal time. Some approaches use matter fields, like a scalar field, to act as a clock. In this setup, the changing value of the field provides a reference by which other parts of the universe evolve. It's a clever workaround, but it still leaves the fundamental question unanswered. Is time real, or just an emergent approximation? What makes all this more than just philosophical navel-gazing is the possibility that these questions might one day be testable. If we can understand how time emerges from timeless quantum gravity, we might also understand what happens at the edge of a black hole, or at the moment of the Big Bang. Places where the fabric of space-time itself tears, and time, if it ever existed, ceases to function. The Wheeler-DeWitt equation, then, is not just a curiosity. It is a key, a doorway. It forces us to confront the limitations of our concepts, and it invites us to imagine a universe where everything we thought was fundamental, time, space, even causality, might be illusions born of something deeper. By the 1970s, physics had reached an inflection point. Quantum field theory had been wildly successful at describing three of the four fundamental forces: electromagnetism and the weak and strong nuclear forces. The Standard Model, once a wild patchwork of particles and interactions, was finally starting to cohere into a masterpiece of predictive power. But gravity, the one force that governed the cosmos at its largest scales, remained stubbornly outside the club. General relativity had no quantum equivalent. It couldn't be tamed by the methods that worked for the others. When you tried to quantize it, the math didn't just fail, it exploded into meaningless infinities. For decades, this incompatibility was tolerated like an eccentric old relative. Gravity was so weak at the particle level that many physicists figured they could just ignore it. Let the cosmologists worry about the universe. But others saw the gap as intolerable. The ultimate goal was a unified theory, a framework that would explain all of nature's forces within a single elegant structure. Without quantum gravity, that dream was incomplete. Then, in the late 1960s, something strange happened. While studying the strong nuclear force, physicists stumbled onto a mathematical formalism involving one-dimensional objects, strings. At first, they didn't seem relevant to gravity at all. But by the 1970s, a shocking discovery changed everything. If you interpreted one of the vibrational modes of a string as a graviton, a hypothetical quantum particle of gravity, the theory naturally included gravity. It didn't need to be added in. It was already there, embedded in the mathematics. And with that, string theory, almost by accident, became the most promising candidate for a theory of everything. The basic idea was as bold as it was beautiful. What we perceive as particles are not point-like dots, but tiny, vibrating loops of string. Different vibration patterns correspond to different particles. A photon is one note, an electron another. The entire zoo of fundamental particles becomes a kind of cosmic symphony. It was an intoxicating metaphor, especially for a generation of physicists raised on the search for unification. And the math was stunning. String theory was not only internally consistent, it demanded it. But there was a catch. In order for the equations to work, string theory required additional dimensions, far more than the 4, 3 space, 1 time, we're familiar with. 10, 11, sometimes even 26. Where were these hidden dimensions? Theorists proposed they were compactified, curled up so tightly that we couldn't see them, like a garden hose viewed from a mile away. From far off, it looks one-dimensional, but up close, it has a hidden circumference. In the same way, our universe might be hiding extra dimensions just beyond perception. This bold leap into higher dimensional geometry transformed string theory into more than a theory of particles. It became a theory of everything. Electromagnetism, the strong force, the weak force, gravity, they all emerged naturally from the way strings vibrated within this multi-dimensional framework. And for a time, it seemed that the Holy Grail had been found, but not everyone was convinced. Elsewhere in the theoretical world, a quieter rebellion was brewing. Some physicists, skeptical of string theory's reliance on unobservable dimensions and lack of experimental predictions, were exploring another path. This movement, led in part by Abhay Ashtekar, returned to the original principles of general relativity and tried to quantize space-time itself, without inventing anything new. This was the birth of loop quantum gravity. Loop quantum gravity, or LQG, takes a radically different approach. Instead of treating gravity as a force mediated by particles, it treats space itself as quantized. At the smallest scales, space isn't smooth and continuous. It's granular, made up of discrete units woven together like a cosmic crochet. These fundamental loops form networks, spin networks, that evolve over time into spin foams. Think of it as the scaffolding of space-time, flickering into existence and recombining billions of times per second. What's remarkable is that loop quantum gravity doesn't require extra dimensions. It doesn't assume anything beyond what general relativity already gives us. And unlike string theory, which needs a background space-time to operate, LQG is background independent. The geometry of the universe isn't fixed. It's dynamic, woven from the loops themselves. This makes LQG, in a sense, even more faithful to Einstein's vision. The battle between strings and loops wasn't just scientific, it was cultural. String theory, with its origins in particle physics, attracted mathematicians, theorists, and physicists captivated by elegance and abstraction. It was deeply tied to supersymmetry and the unification of forces. Loop quantum gravity, meanwhile, grew from the legacy of general relativity, a more geometric, grounded tradition that emphasized conceptual clarity over elegance. And while string theory basked in media attention and academic glamour, bolstered by pop science books and theoretical beauty, loop quantum gravity was more humble, less flashy, more austere. Its community was smaller, but fiercely dedicated. What made the divide even sharper was that both camps operated almost entirely without experimental confirmation. String theory had not produced a single testable prediction. Neither had LQG. Theorists in both camps would argue over papers, conferences, and blackboards, but without data to break the deadlock, the debate often boiled down to taste. Was it better to have a theory that unified everything but relied on invisible dimensions and unknown symmetries, or one that stayed true to general relativity but couldn't quite connect with the standard model? Over the decades, each camp made progress. String theory evolved into M theory, which proposed that strings were just one-dimensional slices of higher-dimensional objects called brains. Loop quantum gravity developed tools to calculate black hole entropy and explore the quantum structure of cosmology, but neither claimed a decisive victory. By the turn of the millennium, the field had fractured into rival paradigms, each claiming a piece of the cosmic puzzle. And while some physicists hoped for a grand synthesis, a way to reconcile string theory and loop quantum gravity into a single framework, most agreed on one thing: the road to quantum gravity would be long, difficult, and full of surprises. As we move forward, the two theories will continue to evolve, cross-pollinate, and challenge one another. And perhaps, in that tension, we'll find the truth. Not in one theory winning, but in the realization that reality is deeper, stranger, and more beautiful than any single framework can capture. If loop quantum gravity sought truth through simplicity, string theory chose a different path, one paved with mathematical grandeur and cosmic ambition. It offered not just a theory of gravity, but a theory of everything. An explanation not only of how the universe behaves, but why it exists in such a strange and beautiful form. For many, it was physics as poetry, an elegant fusion of symmetry, vibration, and multidimensional wonder. And like all good poetry, it raised as many questions as it answered. The core idea of string theory is disarmingly simple: that the fundamental building blocks of nature are not point-like particles, but tiny, one-dimensional loops of energy, strings, vibrating in a higher dimensional space. Each vibration mode of the string corresponds to a different particle. One vibration is an electron, another a photon, yet another a graviton, the elusive quantum carrier of gravity. From this single concept emerges the full zoo of particles that populate our universe. It's an idea that appeals not just to physicists, but to our very sense of harmony. The universe as a cosmic symphony, where particles are notes and the laws of nature are the music theory that binds them. This musical metaphor is more than just poetic. The math behind string theory is deeply rooted in the principles of harmony and symmetry. But that mathematical beauty comes with a steep price. The equations only make sense if the universe has more than the 4 dimensions we experience: 3 of space, 1 of time. Specifically, string theory requires 10 dimensions. Later, M theory, a unifying framework proposed in the 1990s, expanded that number to 11. These extra dimensions are said to be compactified, rolled up so tightly that they are imperceptible to us, hidden in the fabric of reality, like a curled scroll behind the wallpaper of space. To visualize it, imagine a tightrope. From far away, it looks like a one-dimensional line, but up close, you'd see the rope has a circular thickness. An ant could crawl not only forward and backward along the tightrope, but around its circumference. In the same way, we might be moving through 3 visible dimensions, while countless others swirl compactly beneath our awareness. The geometry of these compactified dimensions, known as Calabi-Yau manifolds, determines how strings vibrate, and that in turn determines the fundamental properties of the particles and forces we observe. In other words, the shape of the hidden dimensions dictates the structure of the visible universe. It's an astonishing concept that the quirks of quantum physics and the strengths of forces are encoded in tiny, curled-up topologies beyond perception. But this elegance quickly spirals into complication. There isn't just one way to curl up those extra dimensions. There are trillions. Each configuration gives rise to a different set of physical laws, a different universe. This leads to what physicists call the landscape problem. Instead of predicting one universe, string theory seems to allow a near-infinite number. It doesn't tell you which one we live in. It merely says they're all possible. To some, this is a fatal flaw, a retreat from testable science into speculative mathematics. But to others, it's a feature, not a bug. The idea that all these possible universes could be real leads to the concept of the multiverse. Our universe, in this view, is just one bubble in an infinite cosmic foam, a single strand in a boundless string-theoretic tapestry. M theory takes this even further. It posits that strings are not the only fundamental objects. Instead, it introduces higher dimensional membranes, or branes, of various sizes. We might be living on a 3-dimensional brane embedded in an 11-dimensional spacetime. In this scenario, gravity, unlike other forces, can leak into the extra dimensions. This could explain why gravity appears so weak compared to the electromagnetic force. It's not that gravity is weak, it's that it's diluted, spread thin across dimensions we cannot see. This framework opens up astonishing possibilities. Entire parallel universes could exist just millimeters away, separated from ours by the thinnest veil of dimensionality. Collisions between brains might even explain the origin of our cosmos. Some versions of M-theory propose that the Big Bang wasn't the beginning of time, but a violent brain collision, an interdimensional car crash birthing our universe from the sparks. With this cosmic ambition comes a sobering reality. Despite its elegance, string theory has not yet made a single prediction that can be tested in a laboratory or observed in the cosmos. It remains unconfirmed, suspended in a realm of mathematical abstraction. Critics argue that a theory of everything that explains anything explains nothing. If every Calabi-Yau shape leads to a different universe and all are possible, how do we know which one is real? How do we falsify the theory? Where is the experiment that proves or disproves it? Defenders of string theory push back with passion. They argue that we simply haven't yet built the tools sensitive enough to probe Planck-scale physics, that LHC energies are far too low to detect the minute vibrations of strings. That gravitational wave detectors of the future, or signals in the cosmic microwave background, might one day reveal the hidden fingerprints of string theory's extra dimensions. Some even look to black holes. The entropy of black holes, as calculated in string theory, matches predictions from general relativity. This success is often cited as circumstantial evidence that string theory is on the right track. And then there's the ADS-CFT correspondence, a powerful insight from string theory that suggests gravity in a higher dimensional space can be exactly equivalent to a quantum field theory on its lower dimensional boundary. This idea, holographic duality, has revolutionized thinking in both gravity and quantum theory. Still, string theory remains for now a breathtaking vision unanchored by empirical weight. It may be the universe's great unifying score, a symphony awaiting performance, or it may be a beautiful illusion, a mathematical mirage that will one day yield to a different truth. Regardless of its final verdict, string theory has changed the conversation. It has forced physicists to consider realities far beyond what we can see. It has redefined the scope of what a physical theory can be. And in doing so, it has reminded us that understanding the universe is not just about what we can measure, but about what we dare to imagine. Imagine you could shrink yourself, smaller than an atom, smaller than a proton, smaller even than a quark. Keep going, down past the limits of any microscope, until space itself begins to dissolve beneath your feet. At that scale, near the Planck length, space is no longer smooth, no longer continuous. It flickers, it twists, it granulates. You are standing, if one can stand on such a thing, on the very threads that weave the universe. And according to loop quantum gravity, this weave is not metaphor, it is reality. Unlike string theory, which proposes new entities, strings, brains, and dimensions, loop quantum gravity, or LQG, tries to quantize the universe without adding anything exotic. No extra dimensions, no hidden symmetries, just space-time, as Einstein described it, sliced into tiny quantum chunks. It's a humble theory by comparison, but also an audacious one, because it says, what if space itself isn't a backdrop, but an actor? What if space-time is not the stage, but the play? The roots of this idea stretch back to the 1980s, when Abhay Ashtekar reformulated general relativity using what are now called Ashtekar variables, mathematical tools that allowed physicists to apply the techniques of quantum mechanics to the geometry of space. This shift turned Einstein's elegant equations into something that could finally be probed by the machinery of quantum theory. The result was something astonishing, a vision of space as a network. Imagine a spider web stretched across the universe, but each node and thread isn't made of matter, it is space. These are called spin networks, graphs of loops and links, each carrying a quantum number that describes how space twists and curves. These networks evolve over time, forming spin foams, a kind of four-dimensional fabric in motion. And it's from this ever-changing foam that our experience of smooth, continuous space-time emerges. In this picture, distance, area, and volume are not continuous quantities. They come in discrete units. There is a smallest possible area, a smallest possible volume. You can't divide space forever. You eventually hit the quantum floor. This is perhaps LQG's boldest claim, that geometry itself is quantized, not just matter, not just energy, but space. What does this mean for gravity? It means that the force we call gravity is no longer something that acts upon space. It is space. It is the dynamic choreography of these loops, stretching and shifting, pulling and curving under the weight of mass and energy. When you drop an apple, it's not being pulled by some invisible thread. It's following the geometry of loops beneath your feet, curved by Earth's mass into a path that feels like a pull. This idea isn't just elegant, it's consistent. One of loop quantum gravity's triumphs is that it does not need a pre-existing background spacetime to operate. It's background independent. Spacetime isn't something you put things into, it is the thing. And that's something string theory, for all its sophistication, still struggles with. LQG preserves one of Einstein's deepest insights, that spacetime is a player in the drama of physics, not a passive stage. So far, so good. But how far does this idea go? Can LQG explain black holes, the early universe? The answer is, it tries. In the late 1990s and early 2000s, researchers working in LQG used its framework to calculate the entropy of black holes. According to Bekenstein and Hawking, a black hole's entropy should be proportional to the area of its event horizon, not its volume. Loop quantum gravity not only confirmed this but offered a way to count the microstates that give rise to that entropy using the spin network model. It was an important win, an indication that this granular picture of space could reproduce one of the deepest insights in gravitational physics. And what about the Big Bang? LQG has something to say there too. When you run the equations of general relativity backwards, the universe seems to collapse into a singularity, an infinitesimal point of infinite density where physics breaks down. But in loop quantum cosmology, a branch of LQG applied to the universe as a whole, this singularity is smoothed out. Instead of a bang, there is a bounce. According to this model, the universe didn't begin from nothing. It emerged from the collapse of a previous universe, compressed down to a minimum volume by gravity, then pushed outward again by the repulsive effects of quantum geometry. Time, in this view, never began. It bounced. This is one of the most radical implications of loop quantum gravity, that the universe is eternal, cyclical, and never truly reaches infinite density. Quantum loops protect the cosmos from collapse. They rewrite our origin story. But LQG is not without its problems. For one, it struggles to describe matter. While it quantizes space-time well, incorporating particles and forces, like the electromagnetic field or the Higgs boson, into the framework has proven difficult. It's a great theory of gravity, perhaps, but not yet a theory of everything. And then there's the issue of prediction. Like string theory, loop quantum gravity operates at energies far beyond what we can currently test. It hasn't produced many specific falsifiable predictions. Some hope that future observations of black hole evaporation or gravitational wave echoes might provide hints. But for now, LQG remains elegant and internally consistent, and stubbornly beyond direct observation. Still, what it offers is compelling, a universe where space is not empty, but alive. Where geometry is made of loops, where black holes evaporate not into paradox, but into clarity. Where the beginning of time is not a singularity, but a bridge. In the end, loop quantum gravity is more than a competitor to string theory. It's a philosophy, a commitment to minimalism, to staying true to the principles of general relativity, to building the quantum universe from the ground up, one loop at a time. What if both string theory and loop quantum gravity are wrong? That question may sound heretical to the physicists who've devoted decades to each framework. But for a growing number of researchers, it's not only fair, it's necessary. In the quest for quantum gravity, two dominant narratives have shaped the landscape. But surrounding those giants is a constellation of other ideas, less popular, less polished, but no less ambitious. Each one starts with a different assumption. Each one asks, what if we've been asking the wrong question all along? Take causal set theory. It begins with a radical premise that space-time is not continuous but discrete, and that its fundamental structure is not geometric but combinatorial. Imagine space-time not as a smooth surface, but as a vast collection of events, ordered by cause and effect. A network, a growing chain of atoms of space-time, where one event can influence another, but only in accordance with a strict causal order. This theory, pioneered by Raphael Sorkin and others, suggests that the fabric of the universe is more like a digital simulation than an analog field. Space and time emerge from the connectivity of events. Geometry, in this view, is not a backdrop. It's an emergent property rising from the pattern of causal relationships. Causal set theory makes predictions too. It suggests that the cosmological constant, the mysterious force accelerating the expansion of the universe, might arise from statistical fluctuations in the causal structure itself. It even proposes that space-time grows one atom at a time, a view known as sequential growth dynamics. This is space-time as process, not substance, a universe in perpetual construction. Then there's asymptotic safety. While less visual and more technical, it tackles a long-standing problem. Gravity, when treated as a quantum field, seems to produce infinite results. It's not renormalizable, as physicists say. Asymptotic safety, proposed by Steven Weinberg in the 1970s, offers a way out. It suggests that there exists a safe, fixed point at very high energies where the wild quantum fluctuations of space-time settle into stable behavior. This would mean that gravity can, in fact, be treated like other quantum fields without blowing up into mathematical nonsense. It preserves the familiar framework of quantum field theory while solving one of its most notorious issues. And although it lacks the grand narrative flair of strings or loops, it has the virtue of minimalism. No extra dimensions, no exotic topologies, just good old quantum field theory extended into the ultraviolet. There's also the idea of emergent gravity, the notion that gravity isn't fundamental at all, that it's not a force, not a field, not a curvature of space-time. It's an illusion, a byproduct, something that emerges, like temperature or pressure, from the collective behavior of deeper, non-gravitational degrees of freedom. This is a view popularized in different ways by researchers like Eric Verlinde, who in 2011 proposed that gravity might arise from the entropy of information associated with the positions of particles. In this picture, gravity is not a cause but an effect, a thermodynamic tendency of systems to evolve toward equilibrium. It sounds bizarre, but it fits a larger trend in physics. The idea that space, time, and even reality as we know it may be emergent, not basic, not axiomatic, but the shadows cast by something deeper, stranger, and more abstract. If this view is right, then trying to quantize gravity is like trying to quantize the sound of the ocean. It misses the point. You must first understand the water. Other researchers take this even further. Some work with non-commutative geometry, mathematical frameworks where space does not behave like Euclidean geometry at small scales, and where coordinates themselves fail to commute. Others explore group field theory, causal dynamical triangulations, or even cellular automaton models of the universe. These approaches are diverse, fragmented, and often incompatible. But they share one thing: They reject the dominant assumptions of the mainstream. So why haven't these theories caught on? Part of it is momentum. String theory and loop quantum gravity have large communities, decades of research, and well-developed mathematical infrastructures. Alternative theories often operate on the margins, underfunded, understaffed, and treated as speculative side projects. There's also the problem of falsifiability. Like strings and loops, many of these theories make few, if any, testable predictions. Without experiments to confirm or refute them, the field risks becoming philosophy disguised as physics. And yet, this is where many of the most creative minds in theoretical physics are turning. Not because they believe these alternatives are guaranteed to be right, but because they know the dominant frameworks might be wrong. In a field as foundational and as stalled as quantum gravity, every stone must be overturned. Every idea must be heard. History favors the bold. And while some of these contenders may vanish into obscurity, others might yet rise to prominence. After all, Einstein's own ideas were once fringe. So were quarks. So was quantum mechanics itself. If nothing else, these outsider theories serve a crucial purpose. They force us to rethink, to question our assumptions, to step back and ask, what is space really? What is time? What are we trying to quantize? We don't yet know the answers. But with every causal set, every spin foam, every emergent field and asymptotic fix, we edge a little closer to the truth. Not with certainty, not with consensus, but with courage. We've scaled the heights of theory, wandered through the vibrating strings of a multiverse, the quantum loops of a woven space-time, and the strange causal tapestries of competing frameworks. But now we come crashing back down to earth. Because for all the elegance, for all the philosophical depth, one brutal truth remains. We still have no direct evidence that quantum gravity exists. Not a whisper, not a trace. Just silence at the Planck scale. To understand why, we need to start by understanding just how small and how violent the quantum gravity regime really is. Gravity, as we know it, is famously weak. You can pick up a paperclip with a fridge magnet. That tiny magnet is defeating the entire gravitational pull of the Earth. And quantum effects? They're so small, they typically only dominate at atomic or subatomic scales. But quantum gravity? That's something else entirely. It's the realm where the force of gravity becomes strong enough to require quantum mechanics to describe it. And that happens at a scale so absurdly tiny, it defies human comprehension. The Planck length, 1.616 times 10 to the negative 35th meters. That's a decimal followed by 34 zeros before you even reach a 1. At this scale, spacetime itself is expected to break down into something granular, frothy, or maybe even pixelated. But to probe this directly, you'd need a particle accelerator capable of slamming particles together at Planck energy levels, around 13 tera-electronvolts, or 2.08283 times 10 to the minus 18 of the Planck scale. You'd need an accelerator the size of the Milky Way just to begin exploring it. Not exactly in the budget. It's like trying to see the details of a flea using a telescope aimed at the moon. The scale mismatch is not just inconvenient, it's devastating. Even black holes, which should be perfect laboratories for extreme physics, don't help us much. The smallest black holes we can imagine, the so-called primordial black holes that might have formed in the early universe, are theoretical ghosts. And larger black holes, they're too cold. Their Hawking radiation is so faint it's practically undetectable against the background noise of the cosmos. Detecting quantum gravity effects there is like listening for a pin drop in the middle of a hurricane. Some had hoped that the Large Hadron Collider might produce tiny black holes if extra dimensions existed, as predicted by some string theories. If so, those black holes would evaporate in a flash, emitting Hawking radiation and giving us a direct window into the quantum structure of space-time. But after years of smashing protons together, the LHC has found no such signatures, not a single microscopic black hole, no extra dimensions, no quantum gravity fireworks. And so, we wait. But waiting doesn't mean doing nothing. Physicists have been scouring the universe for indirect hints, subtle imprints that might betray the fingerprints of quantum gravity. Some search the cosmic microwave background, the afterglow of the Big Bang, for telltale anomalies, tiny patterns in the distribution of radiation that might reflect quantum fluctuations in the early universe. Others examine gamma-ray bursts, the most energetic explosions in the cosmos, looking for tiny delays in photon arrival times that might hint at space-time foaminess. These ideas are ingenious, but they're also fragile. Many are mired in ambiguity, drowned in noise, debated to death. Nothing has yet emerged as a smoking gun. Gravitational wave detectors like LIGO and VIRGO have given us astonishing new tools. They've recorded the cosmic thunderclaps of black holes colliding, a triumph for general relativity. But the signals are still classical, beautiful, but not quantum. The waves we're detecting are ripples in the fabric of space-time, but they don't yet tell us what that fabric is made of. Some have proposed that future gravitational wave observatories, like LISA, the Laser Interferometer Space Antenna, might detect Planck-scale echoes in the aftermath of black hole mergers. These echoes would be faint, subtle distortions in the waveform that could arise from quantum corrections to the black hole's surface. But these are speculative and, as of now, unobserved. Even more ambitious are proposals for quantum telescopes, devices that might one day detect quantum correlations between particles emitted by distant cosmic events. These ideas stretch the imagination, but they also reveal the desperation. When you can't build a bigger microscope, you look for natural experiments the universe has already performed. In a way, we are left with a paradox. We have more theoretical pathways than ever: string theory, loop quantum gravity, asymptotic safety, causal sets, emergent gravity, and more. Each with its own vision of spacetime's fundamental nature. But we have less experimental guidance than ever before. We're navigating without a compass. Theory is running miles ahead of observation and beginning to wonder if observation will ever catch up. This is the great frustration of modern physics. We may be living in an age where we understand more about the universe than ever, and yet we're stuck just inches away from the deepest layer. We can hear it breathing. We can feel its weight. But we can't touch it. Not yet. Some physicists worry that quantum gravity will remain forever out of reach, that it belongs not to physics, but to metaphysics, that no detector, no telescope, no atom smasher will ever reach the realm where quantum and gravity collide. Others argue that it's just a matter of time, that a breakthrough in technology, in imagination, in insight, will eventually let us crack the code. But for now, we live in the gap between what we can imagine and what we can prove, between theory and evidence, between hope and humility. And yet, that's precisely where the adventure lies. Because when you can't look outward, you must look inward. When you can't measure, you must rethink. You must reframe the question. You must explore the very edge of meaning itself. And that edge? It sharpens into the next frontier, into the black holes that evaporate into mystery, the paradoxes that refuse to be ignored, the singularities that scream at the seams of our knowledge. That's where we're going next. There is no object in the universe more terrifying or more enlightening than a black hole. At first glance, they're simple, a singularity wrapped in darkness. A region of space-time so warped, so curved, that not even light can escape. They were once considered absurdities, mathematical oddities buried in Einstein's equations. Even Einstein himself doubted they could be real. But then the universe answered back. Black holes are real. They exist, and they are loud. From the gravitational wave booms of binary collisions to the Event Horizon Telescope's haunting silhouette of M87's core, black holes have gone from ghost stories to front-page science. But as we stare into their abyss, They stare right back into the broken logic of our physics. They are the chasm between general relativity and quantum mechanics, and nowhere is that clash more violent than in the mystery of Hawking radiation. In 1974, Stephen Hawking shocked the scientific world by suggesting that black holes aren't entirely black. Using quantum field theory in curved spacetime, a patchwork approach that mixes quantum mechanics with general relativity, Hawking discovered that black holes should emit radiation. Tiny pairs of virtual particles pop into existence near the event horizon. Normally, they'd annihilate, but if one particle falls in and the other escapes, the escaping particle becomes real, and the black hole loses a bit of mass. This is Hawking radiation, and its implications are staggering. First, it means black holes can evaporate. Slowly, yes, painfully slowly. For stellar mass black holes, the process would take longer than the age of the universe. But in principle, given enough time, they will disappear. And when they do, all that's left is what? That leads to the information paradox. According to quantum mechanics, information cannot be destroyed. If you burn a book, the information is scrambled, but in theory recoverable from the smoke and ash. But if you throw a book into a black hole and it evaporates via Hawking radiation, that information seems lost forever. The radiation is thermal, featureless, no trace of what fell in, no record, just entropy. This breaks quantum mechanics. It's not a minor issue, it's a foundational crisis. For decades, physicists tried to ignore it or explain it away, but Hawking refused to let it die, and the paradox only deepened. In the 1990s, string theory offered a glimpse of hope. Calculations of black hole microstates, specific quantum configurations corresponding to a black hole's mass and charge, seemed to preserve information. More recently, the firewall paradox raised new alarms. Maybe the event horizon isn't smooth, as general relativity claims. Maybe it's a wall of searing quantum energy, a firewall that incinerates anything trying to cross. This would destroy the very idea of a smooth spacetime, and with it, the foundations of Einstein's legacy. Meanwhile, quantum gravity researchers kept asking, what does a black hole really look like from the inside? Is the singularity, this point of infinite density, real? Or does it dissolve into something else? A Planck star? A quantum bounce? Could black holes even be gateways to other universes? Loop quantum gravity suggests the singularity might be replaced by a high-density core, where space-time becomes discrete and avoids the infinities. In this view, a black hole could eventually explode, not vanish but bounce, releasing its contents in a new form. Maybe not into this universe, but into another. It sounds like science fiction, but it's grounded in the need to reconcile quantum rules with gravitational collapse. Some researchers propose black hole remnants, tiny, stable leftovers that store the lost information. Others suggest holography, that the information falling into a black hole is encoded on its surface, not lost within. The holographic principle, inspired by string theory and the ADS-CFT correspondence, suggests that a three-dimensional volume of space can be fully described by a two-dimensional surface, a revolutionary idea. Black holes in this view don't destroy information, they store it on their horizon like cosmic hard drives. Still others turn to entanglement. Maybe the Hawking radiation is entangled with the internal states of the black hole. If so, measuring the radiation could reveal the information, eventually. But this clashes with relativity's insistence that nothing can escape the horizon once crossed. We are stuck between two unforgiving truths. Quantum mechanics demands information be preserved. General relativity says nothing escapes a black hole. Something has to give, as so far, neither side has blinked. And then, there's the practical problem. We can't test any of this directly. Hawking radiation has never been observed. Black holes are distant, opaque, and unforgiving. We rely on analog systems, like sonic black holes in Bose-Einstein condensates, to simulate Hawking-like behavior. These offer hints, but not proof. They whisper possibilities, not certainty. The paradox remains. What's certain is that black holes are not just astronomical curiosities, they are the battleground for the soul of physics. They challenge our assumptions about space, time, causality, and reality itself. They are cosmic confessionals where the contradictions of our greatest theories are laid bare. It's no wonder physicists are obsessed. Black holes hold secrets we can't yet decode. They are the crucibles where any true theory of quantum gravity must be tested. If we can understand them fully, we might finally glimpse the unified description of nature we've been chasing for over a century, or we might find that reality itself is stranger than we ever imagined. And as we leave the darkness of black holes behind, we step into another domain where quantum gravity whispers its presence, the early universe. There, in the fraction of a second after the Big Bang, space-time itself was born, and with it perhaps the first clues to how gravity and quantum mechanics danced their primordial duet. Before there were galaxies, before stars lit the void, before even atoms existed, there was only the raw fury of creation. The early universe, an unfathomable ocean of energy, heat, and quantum chaos. It was here, in this incandescent moment, less than a trillionth of a second after time itself began, that the rules of reality were forged. And if quantum gravity is real, this is where it would have left its signature. In the traditional picture, the universe began with a singularity, a point of infinite density, where all the matter and energy of existence was compressed into a zero-volume dot. It's a solution derived from general relativity, extrapolating backward from cosmic expansion. But there's a problem. Infinities in physics usually mean something's gone terribly wrong. A singularity isn't a prediction. It's a warning sign that our equations have broken down. Quantum mechanics hates infinities, and so physicists suspect that, at the earliest moments of the cosmos, space-time wasn't continuous at all. It was frothing, bubbling, and wildly uncertain, governed not by smooth curves but by quantum fluctuations. This is where quantum gravity enters the story. It offers a possibility that the Big Bang wasn't the beginning of time, but a bounce, a transition from a previous universe collapsing inward. In loop quantum cosmology, a branch of loop quantum gravity, the universe contracts to a finite size and then rebounds in a big bounce. The singularity is replaced by a bridge. Time flows through, uninterrupted, yet transformed. Space is never infinitely dense. It is granular, finite, and woven from loops too small for any eye to see. Others imagine that quantum gravity smooths the singularity differently by altering the early universe's vacuum structure or by replacing classical fields with string-theoretic brains that vibrate with multiversal possibilities. Whatever the framework, they share one conviction: something quantum must have shaped the earliest moments. Without quantum gravity, the Big Bang is a breakdown, not a birth. The implications are staggering. At this scale, around 10 to the negative 43rd seconds after the Big Bang, the so-called Planck time, the universe was so hot, so dense, that gravity and the other three fundamental forces, electromagnetic, weak and strong, may have been indistinguishable. Grand unified theories suggest that before symmetry broke, there was a single superforce, and at the heart of this symmetry was quantum gravity, the final unification, the master key to all the universe's forces. If we could understand this moment, we could understand everything. Why particles have the masses they do, why the universe is flat, why it expands the way it does. We could see the blueprint not just of how matter behaves, but of why it exists. And yet the evidence is frustratingly subtle. One major clue lies in the cosmic microwave background, the ancient light that bathes the universe, a snapshot of the cosmos 380,000 years after the Big Bang. It's been mapped with exquisite precision by satellites like WMAP and Planck. Tiny fluctuations in temperature and polarization, quantum ripples inflated to cosmic scales, offer a fossil record of what happened in those first moments. Some theorists believe that if quantum gravity played a role, its effects might be embedded here. Slight non-Gaussianities, anomalies, or unexpected correlations. So far, hints abound. Proof does not. Inflation, the idea that the universe expanded faster than light for a brief instant after the Big Bang, also ties into this search. The mechanism driving inflation likely involved quantum fields, and some models suggest that gravitational waves from this period could carry the fingerprint of quantum gravity. Detecting them would be a scientific revolution. Enter next-generation experiments like the BICEP array and CMB-S4. They aim to find these primordial gravitational waves by measuring the curling pattern of polarization in the cosmic microwave background, a subtle twist in ancient light. If found, and if their structure matches predictions, it could be the first indirect evidence of gravity's quantum side. But again, the signals are faint, and the noise is immense. The universe whispers its secrets in a language we're only beginning to understand. And yet, the early universe also invites a deeper philosophical question. What is time? In general relativity, time is woven into the geometry of the cosmos. It bends, stretches, and flows depending on gravity's strength. But in quantum mechanics, time is an external parameter, a backdrop against which events unfold. The early universe, with no observers and no clocks, forces us to confront this contradiction. Was time born at the Big Bang? Or does quantum gravity demand a more radical rethink? Some approaches suggest that time is emergent, not fundamental, but a byproduct of entanglement or thermodynamic flow. That in the earliest universe, time was not a line, but a haze, a potential, a quantum field of becoming rather than being. These are not just metaphysical musings. They affect our models, our predictions, our search for quantum gravity, because if time itself dissolves under extreme conditions, then our current theories are using broken tools to study the most vital question of all. Still, despite all this uncertainty, the early universe remains the most likely place where quantum gravity left a scar deep enough to be seen, a place where particles didn't yet exist, where space had no shape, and where gravity was not a force, but a quantum breath exhaled into existence.
And as we zoom forward from those first trillionths of a second, we begin to ask, if gravity once danced with the quantum, could they still be partners now? Could they still be united, somewhere, somehow, in the hidden architecture of nature?
That's where we head next, into the heart of unification, into the dream that haunted Einstein, into the idea that maybe, just maybe, all the forces of the universe were once one. Since the dawn of science, we've been in pursuit of unity. From fire and water to atoms and electrons, from Newton's universal gravitation to Maxwell's electromagnetic field, our story has always been one of collapsing categories, of realizing that things we thought were separate were actually the same thing viewed through a different lens. And so it's no surprise that the greatest question left standing is also the most tantalizing. Can we unify gravity with the other forces of nature? Can we finally assemble a theory of everything? That phrase, theory of everything, sounds grandiose. And it is. But at its heart, it's an elegant idea. There are four known fundamental forces in nature: electromagnetism, the strong nuclear force, the weak nuclear force, and gravity. The standard model of particle physics unites the first three. It explains the zoo of particles we observe, the quarks, the leptons, the Higgs boson, with breathtaking precision. But gravity stands alone. It's the outcast, the rebel, the one force we cannot seem to bring into the fold. And yet it must belong. It has to. Because the universe is not made of two realities. It's one. And if gravity and quantum mechanics both describe it, then somewhere, somehow they must connect. Einstein believed this deeply. In the last decades of his life, he became obsessed with unification. He tried to merge gravity with electromagnetism using a unified field theory, an ambitious mathematical framework that, though elegant, ultimately failed. Quantum mechanics, with its probabilities and indeterminacy, made him uncomfortable. "God does not play dice," he famously declared. But nature, it seems, rolls the dice constantly. After Einstein, others picked up the torch. In the 1970s and 80s, physicists developed grand unified theories, or GUTS, models that unite the strong, weak, and electromagnetic forces into a single interaction at high energies. These efforts suggested that at ultra-high temperatures, like those in the early universe, these three forces were indistinguishable, just different aspects of a deeper unity. That was progress, but gravity still resisted. That's where quantum gravity comes in, not as a separate theory, but as a missing cornerstone. If quantum gravity can be found, it could finally allow us to unify all four forces under a single theoretical umbrella. A true theory of everything. String theory, for a time, looked like the answer. Its great insight? Particles aren't point-like, they're tiny, vibrating strings. And the way a string vibrates determines what kind of particle it appears to be. One vibration gives you a photon. Another, a graviton, the hypothetical quantum particle of gravity. In one fell swoop, string theory unified all particles and forces, including gravity, into a single framework. It was beautiful, elegant. It promised the kind of unification Einstein could only dream of. But it came with costs, extra dimensions, 10 or even 11 depending on the version. A landscape of possible solutions so vast it's been called the multiverse. And worst of all, no testable predictions, at least not yet. String theory might still be right, but as of now, it remains an unverified dream. Loop quantum gravity tried a different route. No extra dimensions, no strings, just the fabric of space itself woven from tiny loops. In this model, spacetime is not continuous, but granular, composed of discrete units like the pixels on a screen. This approach doesn't aim to unify all forces, but rather to quantize gravity on its own terms, then find connections later. Some versions of loop quantum gravity hint at deeper links to quantum field theory. But the road to unification remains long. There are other contenders too: twistor theory, asymptotic safety, emergent gravity. Each has promise, each has problems, none has won. Why is unification so hard? Part of it is technical. Gravity and quantum mechanics speak different mathematical languages. Uniting them is like trying to merge poetry with code. But part of it is deeper, philosophical. These two frameworks describe reality in fundamentally different ways. One says the universe is continuous, the other says it's discrete. One says cause and effect reign supreme. The other allows entanglement to link particles across space instantly. At a basic level, they seem incompatible, and yet, nature works. Black holes form, galaxies spin, neutrons decay. The universe somehow reconciles these contradictions, which means the problem is not with reality, it's with us, with our models, our frameworks. We're missing something. What could a unified theory reveal? Everything. It could explain the origin of mass, the mystery of dark energy, the reason why the constants of nature have the values they do. It might even tell us why the universe exists at all, or whether it had to. It could resolve the black hole information paradox, smooth the Big Bang singularity, and reveal what lies beyond the observable universe. A true theory of everything wouldn't just unify physics, it would unify knowledge. It would be the Rosetta Stone of existence. But here's the humbling part. We may never find it. Unification may be beyond our reach, not because it's unknowable, but because we are limited by our tools, our lifespans, our species. There's no law that says the universe must be comprehensible to a hairless ape with a telescope. And yet, we try. Because to seek unity is to be human. To look at the stars and ask not just what they are, but why they are. And if quantum gravity is real, then it's not just the key to black holes and the early universe. It's the key to everything, the secret chord that ties it all together. That's why we keep searching, even when the math fails, even when the data is silent. Because the next breakthrough may not come from a particle collider or a telescope. It may come from a new way of thinking, a new question, a new dream. And so we turn now to the obstacles that remain, the barriers that block the path to that ultimate theory, the cliffs we must climb before we see the full map of reality. There is a strange kind of beauty in frustration, in the stubbornness of truth. For all the brilliance thrown at the quantum gravity problem, decades of the finest minds, mountains of math, super colliders, satellite missions, blackboard wars, the truth still hides behind a veil, and the more we reach, the more it slips away. The pursuit is noble, the obstacles immense. First among them is the sheer incompatibility of our two great frameworks. General relativity and quantum mechanics are masterpieces in their own right. Each explains vast swaths of reality with astonishing precision. General relativity describes the cosmos, the slow dance of planets, the crushing grip of black holes, the ripples of gravitational waves. Quantum mechanics governs the microscopic, the jittery behavior of atoms, the spooky logic of entanglement, the very act of observation. But like oil and water, they do not mix. Try to apply quantum principles to the smooth curvature of spacetime, and you quickly run into infinities. Equations explode, predictions vanish. Gravity refuses to be quantized in the same way other forces are. The universe, it seems, is unwilling to be described by one language alone. Then there's the problem of time. In general relativity, time is flexible, a coordinate that stretches and shrinks depending on gravity and motion. It's woven into the fabric of space-time itself. But in quantum mechanics, time is rigid. It ticks uniformly forward, a background stage against which events unfold. Try to merge these perspectives, and you find contradictions. Does time emerge from something deeper? Is it an illusion? Or does our misunderstanding of time prevent the union of physics' greatest pillars? Mathematically, the challenges only grow. Most quantum gravity approaches lead to equations that are unsolvable, or worse, give too many solutions. String theory's infamous landscape problem is a case in point. It doesn't yield one universe, but 10 to the power of 500 possible ones. Which is ours? No one knows. Loop quantum gravity, by contrast, produces a beautifully quantized picture of space, but struggles to include matter in a dynamic, realistic way. We are trapped between elegance with no predictions and predictions with no elegance. Then there's the absence of experimental data. Quantum gravity is expected to manifest at the Planck scale, around 10 to the negative 35th power meters. That's 100 billion times smaller than anything our current technology can probe. Particle colliders like the Large Hadron Collider are orders of magnitude too weak. Even our most sensitive gravitational detectors like LIGO are tuned to events millions of light years away, not to the microscopic fuzz of space-time. Without data, we are navigating blind. Theories multiply, communities fragment. One camp insists strings are the answer, another champions loops, others whisper of causal sets, holography, or emergent spacetime. Each has promise, none has proof. And so, physics becomes a battlefield of ideas, beautiful, speculative, but ultimately untested. Some call this the post-empirical era of physics, a dangerous phrase, because science at its core is not just the weaving of theories, but their testing, their confrontation with nature. Without that feedback loop, we risk drifting into mathematical theology. Elegant, yes, but untethered from reality. Even our best indirect clues are ambiguous. The cosmic microwave background, black hole thermodynamics, high-energy astrophysics, they all whisper hints, but none scream confirmation. We are left parsing the static, searching for patterns in the noise. Another barrier is conceptual. we may be asking the wrong questions. What if quantum gravity isn't about quantizing gravity at all, but about finding a deeper layer of physics from which both gravity and quantum mechanics emerge? What if space-time itself is not fundamental, but born from something more primitive, information, entanglement, or something we've yet to imagine? In such a case, our tools, mathematics, measurement, metaphor, might be inadequate. We're trying to navigate a quantum jungle with the compass of classical intuition, and the jungle doesn't care about our preferences.
There's also the challenge of scale. Most successful physical theories isolate a domain and describe it precisely. Quantum electrodynamics explains the interactions of light and matter. General relativity governs the curvature of space-time. But quantum gravity, if it exists, must describe all of reality across all scales, from the birth of the universe to the interior of black holes, from the flicker of a neutrino to the heat death of the cosmos. That is a monumental demand, perhaps an impossible one.
And finally, there's the human factor. Science is not conducted in a vacuum. It's shaped by culture, funding, institutions, egos. Researchers stake careers on competing frameworks. Theoretical silos form. Conferences split. Progress slows, not because the questions lack answers, but because the community lacks consensus. The best ideas may never see the light of day, not because they're wrong, but because they're ignored. Still, we persist. Because the dream of quantum gravity is not just to explain how the universe works, but to understand why it exists at all, to glimpse the source code, to peel back the veil. Every barrier, every setback is a challenge, not a defeat. And perhaps that is the most humbling truth of all, that we are not entitled to understanding, that nature does not owe us a final answer, that some things may remain beyond the reach of minds shaped by evolution to hunt, gather, and fear the dark. And yet we look anyway, because behind every wall is the echo of a deeper truth. And somewhere, just past the horizon of what we know, lies a theory that makes it all make sense. We stand at the edge of knowledge, peering into a mystery that refuses to yield, yet refuses to let us go. Quantum gravity is not just a scientific problem, it's a mirror, one that reflects the limits of our imagination, the persistence of our curiosity, and the unfinished nature of our story. And as we stare into the deep unknown, a single question hangs in the silence. What comes next? The answer lies in the skies above us, and in the machines we build to listen to them. Right now, scientists around the world are preparing for the next era of observation. One of the most ambitious missions on the horizon is LISA, the Laser Interferometer Space Antenna. Slated for launch in the 2030s, it will stretch 3 spacecraft across millions of kilometers, forming a triangle in space that can detect gravitational waves from sources billions of light-years away. Not just the crashes of black holes, but the soft tremors of the early universe itself. If the fabric of space-time carries the fingerprints of quantum gravity, LISA may be the first to catch them. Other efforts aim to map the cosmic microwave background in even greater detail, looking for subtle patterns, anomalies, or tiny deviations that could signal new physics. The faintest fluctuations in this afterglow of the Big Bang may hold echoes of a time when quantum mechanics and gravity were one. If we can read that ancient light with more precision, we might glimpse the quantum past. On Earth, particle accelerators continue to push boundaries. The Future Circular Collider, a proposed successor to the LHC, could probe energies never before achieved in a laboratory. While still below the Planck scale, new anomalies, particles, or symmetries might emerge, breadcrumbs pointing toward a deeper theory. Then there's quantum computing, not just a tool for breaking codes or simulating molecules, but perhaps someday for simulating quantum space-time itself. Some physicists believe that the fabric of reality is encoded in quantum information. If so, then quantum computers might become our first microscopes into the quantum structure of the cosmos. And yet, the most promising frontier may not be in machines, but in minds. New generations of physicists, untethered from old assumptions, are reimagining what quantum gravity could mean. They speak of emergent spacetime, where geometry itself is not fundamental, but arises from networks of entanglement. They explore the holographic principle, where the information inside a volume of space may live not within, but on its boundary. They question whether gravity is even a fundamental force at all, or a side effect of entropy, thermodynamics, or the flow of information. These ideas are radical, speculative, but so is relativity, so is quantum mechanics. Every paradigm shift begins as heresy, and then, if it fits nature, it becomes fact. Still, we must tread carefully. The path forward is not paved in certainty, it is fogged in mystery. Many of our brightest ideas may be wrong, but that's the risk we take for discovery. To find the answer, we must first ask the question, and ask it boldly. Will we ever find quantum gravity? A final theory, a unifying equation that captures the dance of particles and planets in a single stroke? No one knows, but maybe that's not the point. Maybe the point is the journey, the striving, the endless beautiful process of peeling back layer after layer of the universe, only to find there's always more. Maybe it's in the effort, in the curiosity, that we become more than what we are. Quantum gravity may be the holy grail of physics, but it's also something more. It's the ultimate campfire story. A tale we tell ourselves to remember what it means to wonder. Because the universe didn't have to be this strange. It didn't have to be quantum. It didn't have to be gravitational, but it is. And here we are, on a small planet, orbiting an average star, in a galaxy among trillions, daring to ask how it all works. So we will keep building, keep testing, keep imagining. We'll listen for whispers from black holes. We'll measure the tremors of the Big Bang. We'll trace the path of entangled particles across the vacuum of space. We'll do all of this not because we must, but because we can. Because asking is in our nature. Because understanding is our inheritance. And perhaps one day, in a lab or a satellite, in an equation or an insight, the answer will come. And when it does, it will not just explain the universe. It will show us who we are. This is Frontiers of Infinity. And this is just the beginning. Thank you for joining us on this extraordinary journey through the universe here on Frontiers of Infinity. If this glimpse into the unknown has sparked your curiosity, be sure to subscribe and join us each Friday at 7 p.m. Eastern, where we unravel the darkest mysteries of space.